Okay, now let's define normed vector spaces. We'll start with a vector space E. Vector spaces are also called linear spaces. And if you don't know what it is, you need to look it up. We start with E, a vector space, and we go to R, and we define a function n from E to R. N will be a norm if it meets some criteria. The first one is that n of x equals 0 if and only if x is equal to 0. So you start with an element in E, in the vector space, which is usually called a vector because it's a vector space. So you start with an element x, a vector, and n of x is 0 means x is equal to 0. And conversely, if x is equal to 0, then n of x, in other words, n of 0, is equal to 0. That's the first criterion. Second criterion is if you choose a vector x and you multiply it by a number, lambda, then n of lambda x will be equal to the absolute value of lambda times n of x. That's the second criterion. And the third one is that n of x plus y is smaller than n of x plus n of y. And by the way, if you have the second and the third criteria that are met, then obviously you have n of x positive. If you have all of this, then E is a normed vector space. E with n as a norm is a normed vector space. And n is usually noted with 2 bars, and sometimes with an index you put E, so there is no confusion. That is the definition of a norm, and that is the definition of a normed vector space. If you don't have the first criterion, then what you have is a semi-norm. And you have, nevertheless, n of 0 equals 0, thanks to the second criterion. In this case, you have a semi-normed vector space. I'm going to give you an example. Let's start with the set of all bounded sequences, which is usually denoted L infinity. In this set, you have 1 over n, that's a bounded sequence, but you don't have n squared, because n squared is not a bounded sequence. It actually goes all the way to plus infinity. So I start with this set, and you can verify that it is a linear space, a vector space. You can verify this. I will define n this way. The supremum of all of the absolute values of ui. Question is n a norm on L infinity, on E? First criterion, n of u equals 0 if and only if u is equal to 0. Well, if n of u is equal to 0, it means that the supremum of all the ui's is equal to 0, which means that all of these ui's, the absolute values of these ui's, is equal to 0, which means that the sequence is 0, 0, 0, 0, 0, 0, 0, all the way to plus infinity. So what we have is that n of u equals 0 if and only if u is equal to 0. Second criterion, n of lambda u is equal to absolute value of lambda times n of u. Well, that is the case, because n of lambda u is equal to the supremum of the absolute values of the lambda ui's, which is also the absolute values of lambda times the absolute values of ui's, which is the same as the absolute values of lambda times n of u. So for any real number lambda, n of lambda u is equal to absolute values of lambda times n of u. And third criteria, n of u plus v is smaller than n of u plus n of v. And when you add up two sequences, you basically add up every terms of the sequence. So n of u plus v will be the supremum of the absolute value of ui plus vi, which is smaller than the absolute value of ui plus the absolute value of vi. So when it comes to supremum, what you have is that this is smaller than the supremum of the ui's plus the supremum of the vi, and therefore n of u plus v is smaller than n of u plus n of v. Therefore, En is a normed space. Another example, or actually another infinity of examples. The norm P and the norm infinity defined on Rn. Well, first of all, Rn is obviously a vector space, and I can define the norm P as the pth root of the sum of all the components of x raised to power p with an absolute value, which, by the way, is the distance dp between x and 0. And I can define the infinity norm as the max of the absolute value of each component, and that is also the infinity of x0. So these are examples of norms in Rn, and you can actually have the proofs in the PDF document which is attached to this lecture. I would like to ask you this question. E being the set of functions from R to R defined in 0, can I define the norm f as the absolute value of f of 0? Is this a norm? The answer is no, because if you look at the value of x squared in 0, that is 0, but the function itself is not 0. So this is not a norm.